All right, so let's take a look at what we got. So basically, we need to have the hydrogen which is bonded to like O, F, or N, right? So that's like a good point here. So basically, oxygen, fluorine, and nitrogen, right? So we need to have those bonds, which we have in this case, right, in our molecules in front of us on this paper, right? So now, laptop, come on, right? So, and then, yeah, that's it. So now we are going to take a look at the bonds, right? Such as like OH, for example, right? So maybe let's make it different, right? For example, like red here. So that one, HF and NH bond in this case. So now the next kind of like notion that comes to mind, it's going to be the differences in electronegativities, right? So in all those cases, oxygen, fluorine, or nitrogen are more electronegative than the hydrogen, right? And then we can think about the pool of this like electron density towards the more electronegative atom, right? So we can maybe show it with the arrow, right? Saying, okay, well, the electrons will be moved towards the more electronegative atom. So it is just like from the periodic table, right? You can think about the trends and then hopefully recall that like nitrogen, oxygen, fluorine will be more electronegative than the hydrogen, which is like more to the left in relation to NOF. So now in this case, you are going to have this situation, right? So and then this can also be shown in terms of the charges, right? So charges will be known as deltas, right? So that will stand for the partial charges. So then in this case, we are going to take a look at this, right? So let's maybe assign those partial charges. And then I'm going to look at the NH3 ammonia molecule in this case, and I'm going to do something like that, right? So let's put it this way. So it's going to be delta plus and delta minus. So partial negative on the nitrogen, partial positive on the hydrogen, right? So now let's take a look at the water molecule, for example, and here I go. So what if I'm going to say something like that, right? So, and now it's going to be like this. Okay, so now let's kind of like be a little bit critical here. And now, so next question will be asked. So in this situation, the question will be like this. So like, everything does everything look fine? So does everything look fine in this representation, right? So you have some kind of like a scheme, right, on this paper right now. So does everything look fine in this case or not, right? So and then if not, then what should we correct? So because those partial charges are delta plus and delta minus for a reason, right? And the reason being differences in electronegativities. So electronegativity, it is the ability of the atom to like pull the electrons towards itself, right? So because maybe it will have like a large nucleus, right? Which consists of protons, right? Which are positively charged, so they will be able to attract the negative charges, right? It is just a physics argument in this case. All right, so now let's see if everything looks fine here or maybe not, right? And if it's not good, then we'll need to correct it somehow. So let's see. So what's happening? So it is like NH3, perhaps it's fine, right? So, but what about like HF and H2O? They have kind of like the same charge distribution pattern, but is it right? So that's going to be the question now. Okay, so now let's take a look at what happens. Okay, great. Thank you for your effort here. So then basically people say the charges are switched, right? So that is what was wrong here. So doesn't look right. So H needs to be positive. So here are specific corrections. So this is going to be the case. H will be positive, right? And now we have another person with the responses, right? F and O should be partial negative. So that's going to be the case, right? So you are correct. So since oxygen is more like electronegative, it will have the delta minus. So that's going to be the huge minus here, right? So, and then Fluorine is also partially like more electronegative. It will be having delta minus charge. So by extension, H in both cases will be partially positive, right? It's going to be like a positive sign here, delta plus, but they're also partially positive, right? And then if you think further, right, about dissociation, right, when the bond breaks completely, you will make the ions, right? And then this will give you the way to assign the charges to H plus, which will be H plus, and the positively charged like hydrogen atom, which is the proton in other terms, and then you will have like OH minus or F minus, right? So something to think about further when you think about dissociation. Okay, so now finally, let's take a look at the like alcohols here, right? So what's happening? So like alcohols and their properties, right? So they will have this, like from the geometry perspective, they will have the so-called bent shape, right? So because why? So if we take a look at the okay, so that's the hydrogen here. So if we take a look at the geometry of this molecule, we will realize that, for example, oxygen atom has the, as we call it in general chemistry, four things around it, right? So we have the like R. R will stand for some sort of group, right? So typically R stands for an alkyl chain of some sort, unless it is otherwise specified, right? So maybe R can be like phenyl, or maybe like for now, let's imagine that R is, for example, like ethyl, right? Or propyl, or maybe isopropyl, right? So it could be like anything because it's like literally could be considered as like a random group, right? So in this case, for your like review purposes, you can just imagine, okay, R, let's say it will be butyl, right? What is butyl? So maybe it's going to be a good idea to like draw it, right, on the side, and then you will make not just like ROH, but you will make one butanol, right, according to the nomenclature of alcohols. So the shape here will be bent, so because we have like directly attached what? So if R, let's say, is butyl, then oxygen will have to be attached to the carbon atom, right? So we'll have carbon, oxygen H. So this will mean that we have like two like physical atoms attached to the oxygen, and then that's what will make this kind of like bent shape, right? So and the shape will be bent because and it cannot be linear since we have two more things attached to the oxygen. So those are counted as things, right, which are attached to this kind of central atom, for which we try to figure out geometry. And technically, if you think about the spatial distribution of all the four things, which are R, or carbon atom in this case, right, with its like respective ramifications, then lone pair, and hydrogen. So you'll have four things around the oxygen. So technically, it can also be considered the tetrahedral shape, right? So it's going to be tetrahedral arrangement of the substituents which are attached to oxygen, right? Just like you imagine maybe like methane molecules, so it's going to be tetrahedral, as we know at this point. So, but since we only have like physically carbon, which is going to be part of the R group, and H, so we will like end up having the bent shape, right? So it's going to be kind of like some physical oxygen and another H atom, and then they will end up having the bent shape. So I'll kind of like bring the molecular model next time. So then what else? So they're polar, right? So like for the reasons we just explained here. So we have the high difference in electronegativity present between the, for example, oxygen and hydrogen atom, right? So that's why they are marked as delta minus, delta plus, respectively. And also, as at least some of you told me in the Google Classroom, so we have this OH bond present in the molecule of alcohol. So consequently, we'll be able to experience hydrogen bonding, right? So, and then if we take a look at the physical properties, right? So, because sometimes it's going to be a good idea to go from micro level to the macro level, such as, okay, well, what about the IMFs, right? So which are kind of like between the molecules, right? So on the like micro level, so then how do they influence something kind of like larger, right? So from here, we can think about the famous physical properties such as boiling point, right? So apparently, if you like recall from like Gen Chem, so let's say water has a high boiling point, relatively speaking, right? So amongst like various commonly used compounds, right, or liquids, for example. So it has like 100 degrees Celsius, right? So it's pretty high compared like with other compounds. And then the reason for that is that water is capable of hydrogen bonding. So if we take a look at butane and 1-butyl, try to compare their BPs. So then for butane, it's going to be extremely small, right? So it will boil at like already like 0 Celsius, for example, right? So today we had what in the morning there was like 39 or something like that, at like 7:30 a.m., right? So which is pretty close to like maybe like 5 Celsius or something, right? So then butane will already boil, right, at like 39 Fahrenheit or about like 9 maybe Celsius, whatever the conversion is, right? So, but if we take a look at the butanol, which is just going to be also 4 carbons, but with the OH group attached, then we'll have a dramatic increase in the boiling point, right? So it's going to be like 117 something Celsius because we have the hydrogen bonding, right? So that is something to keep in mind. So hydrogen bonding will help the molecules stay together, right? So consequently, it's going to be more difficult to separate them. So if you think about butane, it's only dispersion forces. If you think about butanol, it's dispersion forces plus hydrogen bonding. So you'll have more ways to connect the molecules. So consequently, higher temperatures to break them apart. So and now these are kind of like some examples, right? So what you can see, if you take a look at the molecule of, let's say, ethanol here, right? So this is going to be, for example, here, we can see the R group being, for example, the ethyl, right? So purple circle. So this is going to be considered as your R group, right? If, let's say, you keep, for example, like drawing the ethanol molecule, right? Maybe like 10 times, right? At some point you can say, well, so I'm not going to like draw ethyl 10 times because at this point I'm like professional, right? Or you're professional rather in drawing the ethyl group, hopefully in various ways, like expanded, condensed fashions. So then you can just call it R, right? So that's going to be fine. So because at this point, so this group doesn't directly participate in the reaction, right? So it's going to be basically the focus here is on the OH group. So that's what kind of like gives us the hydrogen bonding capability, right? So and then here we have the bonding, right? So which is the hydrogen bonding indicated by the dotted lines, which is present between the O and H, for example. So the reason here is perhaps going to be highlighted in activity number 1, right? So which is going to be a little bit kind of like the expansion, right, of this drawing on the right. So because once you show the partial charges correctly, you'll be able to like say, well, that's why the hydrogen bonding is between O and H, but not between like O and O or H and H, right? So yeah, that's just kind of like something to keep in mind. And then plus like more physical properties, right? Examples. So we have like very similar structured like alkane chains, let's say, right? So except this like alkane chain will now have the like OH, the hydroxy group, right? Which makes it alcohol because we have carbon OH kind of a connectivity pattern. So then we have a dramatic increase in the boiling point again. So just another structural example. So, but now let's get to activity number 1. So now it's kind of your turn to work, so to speak, right? So here you have it, right? So alcohol of your choice, 2 molecules of an alcohol of your choice, right? So don't kind of like delve into the water or carboxylic acid just yet, right? So, and maybe show at least like, I don't know, like 4 carbons, right? So let's say maybe the 3. So then here you need to show the hydrogen bonding between your alcohol molecules, but also with the partial charges, right, on the respective atoms. So that's what you'll need to do. And for the drawing, so let's say it's going to be, let's make 4 carbon atoms, and then you will need to show the expanded. Let's go with the expanded structure because you have condensed here, so it's going to be kind of like unfair, right? So, but for activity number 1, you have that. Okay, so we have, so you go. So activity number 1, we'll try to give way to the people who didn't do it that much, right? So, but now it's time to switch the paper. So you have the color choices there, and yeah, take it away. All right, so alcohol of choice in grades looks like we can go with like 4 carbons, right? 4 carbons in the alcohol and expanded structure, right? So because here we already have the condensed, so we want to show the bonds, right? So which is what is being done right now. Okay, so we have here 2 carbons. So well, it's ideally make it 4, right?
Should I make it 4 right now?
Yeah, add 2 more carbons. So that's fine.
To this one?
Yeah, yeah. So you can just like draw over. So that's okay. So make it like, yeah, not ethyl, but yeah, and then continue. Okay, great. So it's going to be just like a B2, right? But don't forget your H's, right? So because the drawing should make sense. So, and that's what we have here. So we have CH3, and then we have 3 more CH2, right, in a row. And then we have the OH. Okay, good. So, and now that's going to be kind of like spatial arrangement, right? So which is what you will need to like show in your drawing correctly. So that's it, right? So the 2 identical alcoholic molecules. Good job so far. It's being done, right? So the hydrogen bonding is typically signified with the dotted line, right? So, and then this is our expanded structure, right? So, which is another like, fulfillment of the requirements, right? So, but now we show the partial charges correctly, right? So that will exist. Okay, good color code. Okay, so yeah, there will be pluses, but what do we need to, what's the letter for the partial, right? So it's a Greek letter. Looks like,
a little thingy.
yeah, looks like B, but it's delta, right? So it's a delta plus.
Oh no.
Yeah, let's try to do the delta. It looks like B, but not quite.
I swear I know what it is. Hold on.
All right. So it's a new alphabet, perhaps, but yeah, eventually, like you might as well like, need to do this on the exam, right?
Oh, that doesn't look good.
All right, great. So yeah, that's fine. It's going to be like a delta plus. All right. So where's going to be delta minus at, right? So,
the 2 O's.
On the oxygen, like show there, it's going to be delta minus. It goes like left to right. Okay.
Like the matter student.
Delta minus, great. So yeah, and then finally another delta minus on the other like molecule of alcohol. Yeah, that's the one, right? And then you have delta plus, and that's it. So now you have literally like 2 charges, delta plus and delta minus, next to one another. So that's why you will have the hydrogen bonding, right? So they will attract. So delta plus on the hydrogen, delta minus on the oxygen, right? Plus and minus will attract. And then, yeah, so that's a pretty comprehensive drawing. So like, well done. So then, yeah, we can now move on officially. So now let's see what happens here. So these are just some examples of the hierarchy of boiling points, so to speak, right? So let's take a look at, for example, like a case B, right? So in this situation, let's take a look at this like mini exercise, case B, right? So you have alcohols 1, 2, 3 arranged like that. So well, rather you have like alcohols 1 and 3, but you have alkane, which is number 2, right? So we need to count the carbons, right? It's going to be like a particular number of carbons everywhere. So, and we also need to take into account the OH group's existence, right? So let's take a look at part B, and then let's try to arrange them in the boiling point. So boiling point increase, let's do it this way. So that's going to be the, okay, so highest, okay, which alcohol in each group would have the highest boiling point and why? Okay, so let's take a look at actually case B. And yeah, it's going to be the question here. So create question. All right. So finally, so B. So which one? Why? Okay. So it's going to be a little bit of the explanation here, right? It's a why-based question for you. So you have here the compounds 1, 2, 3 in case B. So, and then we need to like decide which one will have the highest boiling point. I would say that there are like two arguments that you can draw, so to speak. If you compare, for example, like 1 or like 2 and 3 with one another, so you'll be able to like make a judgment here. All right, so yeah, looks like it's back. It might die, so we may need to make a switch. Okay, so let's see. Once again, right? All right, so anyway, so we have a little bit of the like answer going on, unfortunately, but it's fine. So we need to explain why, right? So that's not on the slide. Okay, so let's see what we have. So we have some responses going on already. So, okay, so yeah, basically here we have the choice for 1, okay, that will have the highest boiling point. And then why is that so, right? So because it has the OH group, right, which will be capable of hydrogen bonding, just like Megan was showing to us. So that's what will happen, right? So like in case of 1, except you have just a different tail, right? It's going to be not 4 carbons, but 1, 2, 3, 4, 5, 6. 6 carbons it will be, right? So it will be like a pretty long chain, right, of carbons, like high molecular weight. And then it will also have the OH group present, capable of H bonding, and then, yeah, relatively longest carbon chain. Okay, that's 2 points of comparison. Okay, so like well done. So now let's see. And then, yeah, if we take a look at case A, we are going to have here, like I'll just explain, this is going to be the winner, right? Highest boiling point for the linear alcohol. So these alcohols, 1, 2, 3 in case A are all alcohols, right? Because you literally have the OH group or hydroxy group. Some people are asking about that. So can we use it interchangeably? If you just look at OH by itself, it's called hydroxy group, right? So once it is in the organic molecule attached to the carbon, it's going to be part of the alcohol group. Like COH will be your alcohol group, kind of like functional group. All right, so here, like 3 will have the highest boiling point because it's most linear, right? As I recall, like linear compounds can kind of pack more tightly, and then this will kind of increase their connection between the molecules. It will be harder to separate them. So plus we have the OH group, which will be kind of like the not a decisive factor, so but decisive factor here will be the branched versus no branched, right? So if the structure is linear, it will have higher kind of cohesion and higher boiling point to separate those cohesive molecules. All right, so now let's get to the, so that's the table, right? So that kind of compares, right? So like alkenes versus like alcohols. So yeah, basically what is going to happen is that if you have like a relatively, so that's going to be about the solubility already, right? So we are going to take a look at the solubility. So it is essentially comparing the alcohol with water, right? So if you look at the alcohol, it could be like that, right? So like OH and some kind of like relatively long carbon chain, right? With 4 carbons, for example. So, or maybe you will have a look at another alcohol, which will be like this, right? It will also have a OH attached to the carbon, but maybe we're going to have like here, let's make it CH2 and CH3, like this, right? So this is going to be like a shorter chain alcohol. So in this case, what happens according to this table, so if you have a shorter chain alcohol, it will have a higher solubility in the water, right? So because if you look at this, right, so this compound, for example, this is ethanol or butanol, right? So that's what we have here, 1-butanol, that's the one, by the way, in the drawing. So they're kind of similar to water, right? So they both have the OH group, and now we only have one difference, right? So water will have like HOH, but alcohol will have HO, and like here it is ethyl group, right? Or maybe butyl. So they're kind of close to water, right? So because we have not so much of the change, we change from the hydrogen to just a couple carbons and like 5 H's, right? So, but if you look at, and then you will have a higher solubility because it is like water, like dissolves like. But if you go to like one heptanol, right? So heptanol is supposed to have the OH, and then this chain would be like this, but with 7 carbons, right? So you need to basically show one heptanol, which will be containing 7 carbons, right? So this is going to be a much more higher difference, so like a larger difference from the water molecule. Consequently, it will be more like heptane, for example, right? More like alkane, and it will be less soluble in water. So if you take a look at some kind of like molecule, let's say OH, right? So we'll have OH here, let's say, and now we are going to draw a huge chain, right? Which consists of however many carbons I'm going to draw here, right? So that is a lot of carbons. So this is like very much different from water compared with this molecule, right? Consequently, this is much more likely to be like an alkane, right? Solubility wise, and then this will be like not so much soluble in water, which is shown in this page, right? Or this table rather. So yeah, just something to keep in mind, some trends, right? So now what else? There's just some examples, right? So like in other words, we can call this like high carbon chain and hydrophobic chain. So basically it is afraid of water, and then it will like impart low solubility to the alcohol with a huge carbon chain. All right, so now let's see, let's take a look at some kind of other cases perhaps, right? So if you have, let's see, so here, so we are going to take a look at case C and D, right? So in both the situations, we are going to have OH groups, right? And what's going to happen next is that, let's say we are going to have here, okay, that's going to be 1, 2, 3, 4, 1, 2, 3. Oh, sorry. So yeah, this, right? So let's take a look at situations C and D specifically, right? So that's going to be our focus right now. So in this case, okay, so if you think about the solubility, right? So which compound, C or D, will have a higher solubility in the water, and why? So they're kind of similar, right? So they do have similarity points if you count the carbons, right? That's hint number 1. But also they have differences, right? Which are also kind of like visible here, right? Between structures C and D. So now I'm going to ask this question to the classroom in the like Google. All right, so material, what's happening? So question. All right, so C or D. So which one has the higher BP and why, right? And why? So that's oftentimes the question that we'll need to like answer, maybe in research, right? If you start doing that all of a sudden, so, or at some kind of like work situations, whatever it might be, right? Related to like medicine or nature, veterinary stuff, right? Whatever your like major will be. So let's try to think about the why question, but in case of like C and D, right? Comparison. So yeah, pretty like isolated, but still. So why is one will have the is going to have a higher boiling point than the other, right? So like what is happening? So we have the same number of carbons, right? So if we at this point look at our like skeletal structure drawing skills, it's going to be okay, like 1, 2, 3, right? Bend, bend, terminus. So then you have like 1, 2, 3, 3 bands basically, so also 3 carbons. So but what is different, right, that makes the differences in solubility? Okay, so let's take a look. Okay, so basically people say it's going to be D will have a higher solubility in water, right? And then because of 2 OH groups, right? And now we basically have here like a nice like argument. It's going to be 2 H bonding groups instead of 1, right? So that basically you are going to have like more H bonding capable groups, right? And then you'll have more hydrogen bonding. So between the molecules. So the more H bonding there is, the harder it is to separate them, right? So if you think about some kind of hypothetical alcohol, maybe it's going to be like OH group here, right? Let's imagine that. Then it's going to be even higher boiling point, right? So yeah, just kind of something to keep in mind about the trends, right? So trend thinking. So that's potentially going to be useful, not only here, but like in general, right? So try to make it kind of like practical. All right. So now let's see. So here we go. So reactions, right? So finally, we are going now to take a look at not only the formation of those hydrogen bonds, which are bonds still, right, that can be formed. So, but you see, as it was shown, so we have literally here the dots, right? So they're not quite like covalent bonds, which are shown with the lines, right, solid lines. So those are called electrostatic bonds, right? So that's what that's how we describe the hydrogen bonds. They are electrostatic in nature. They're not covalent, right? Covalent versus electrostatic, different terms, right? So and then, yeah, this is going to be kind of like not quite a reaction, right? So it's going to be just kind of the electrostatic attraction or interaction between the two molecules, right? So because basically, so that's like attraction between the opposite charges, like from physics, right? So there is no like breaking of the bond and then like something new is created, right? So now let's take a look at the reaction. So this is just going to be like a verbal classification, right? So we have dehydration to yield the alkene, right? So that's why we wanted to connect terms to like structures, right? Because here you go, right? So dehydration, what is that, right? So that's like when we remove the water molecule, for example, right, from our compound, and then we make the alkene. So then later on, we'll take a look at the new class of compounds, which are going to be like ethers, right? But at least at this point, we should be familiar with the functional group, right? What the ether looks like, right? In terms of the arrangement of the like, carbons and oxygens. So and then oxidation to yield the carbonyl compounds, right? Oxidation is basically when you subject your compound, alcohol in this case, to like oxygen, reaction with oxygen, right? So maybe when, for example, you burn carbon, right? So in oxygen, it's also oxidation, technically. So, and then you here make carbonyl compounds. Maybe like carbonyl will be like a good functional group to recall because it's going to be, like, again, one of those common functional groups, which we see from day one pretty much, or exam one until the final exam, right? So, but now let's take a look at some specific reactions here. So, and then they can be classified as synthesis. That's when you make alcohol, right? So sometimes you can be like, okay, well, start with some sort of alkene and make alcohol out of that. Well, that's how this happens, right? So yeah, basically you can take alkene, add water to that, and then you will make alcohol. So, so in this case, so this will be called, this is going to be called the hydration reaction because you add water, right? So just like in the human consumption of water, so if the person hydrates, right, for like whatever reason they want to like achieve, so they will add the water to themselves. So same happens with alkene, right? You start with an alkene, you add water to that, then you'll make alcohol. So it's going to be just a general scheme, right? But here, pay attention to some specific things, such as this one, right? So that's going to be your catalyst, right? Catalyst, H2SO4. So it falls under the conditions of the reaction, right? So it's going to be kind of like necessary to show it, right? So even if it's not asked, so like for the proper hydration reaction to occur. So in case of alkenes, right, not the people, humans, you will need to use H2SO4 as a catalyst. Let's just put it this way, right? So we need to kind of remember this, but why this happens, we kind of like don't care about this just now because it's an introduction to organic chemistry, right? So dehydration, so this will be what? I'll make the green colors. So this is apparently the opposite situation, right? That's when you remove the water molecule, right? So from the alcohol to make alkene, right? So conditions also, like pay attention to that, right? So that's something to remember. H2SO4 kind of like will still be used, surprisingly enough, right? Plus, it's going to be at relatively high temperatures, just like if you, let's say, run like 2 miles, like and sprint a little bit, so then you will like sweat, and that's going to be the dehydration, right? They are exemplified so by sweating and such. So the water will be released. So here, so if you want to show it, right? So you think about, okay, like the human sweats, right? And there is like a skin, and then on the skin there will be like a sweat formed, right? So here you have the same situation, similar situation. You start with the alcohol. subjected to the conditions of dehydration, and will make alkene, and the water, right, will be released. So if you want to show that something is released or produced, right, kind of like chipped away from the molecule, then we can show it on the product side, right? Sometimes people show like alcohol minus H2O becomes alkene, but don't do that, right? So that's like not conventionally accepted. So we always like use pluses in chemistry, right? If you want to show something getting out, just show it on the product side, right? So then it will bear the plus sign, alkene plus H2O. So now example dehydration. So here you go, right? So we now look at the specific molecule, right? So and here we go. So that's what will happen. So you are going to form from the alcohol, you are going to form the alkene, right? So here, if you look at the count of the like atoms, so basically you remove the water molecule, you remove a HOH. So, and then you can show it. So if we want to be completely kind of like holistic here, so let's show the HOH molecule as a result, right? So yeah, basically, so think about this, like OH is removed, right? And then one of the hydrogens is removed. And now you have CH2, CH2, if you imagine that, so that will happen, right? So you are going to have CH2, CH2, and they will have to be connected with a double bond, because if we just, for example, show somehow in a like hurried fashion, like CH2 and CH2 like this, right? That's going to be bad, right? So because it's going to be, okay, well, carbon with only 3 valences, right? Out of 4, what happens with the like other valence, right? So that's kind of like not a good business. So here you have a tetravalent carbon, so all proper, and you have alkene, right, which is supposed to have the carbon-carbon double bond anyway. So now let's take a look at like what happens like in reality, right? So this is dehydration of 1-propanol. So in this case, we're just going to show properly all the like bonds in the molecule. So that's why we ask, like I ask you, right, to show the expanded structure, right? So here's the one, right? So we have all the bonds shown, maybe even like more than needed. So, but it's okay, right? So this like practice will like not be like damaging or something like that, right? So, and so what we're going to do is show like which bonds are going to be broken, right? So let's take a look at the part, right, which contains OH and hydrogen, right? So basically, in your alcoholic molecule, you'll need to find the carbon with OH, right? And then you need to find not just any other carbon with a hydrogen, right, like randomly, but you need to identify 2 adjacent carbons, right, which is basically going to be, let's make them green, right? Green carbon here and there, right? So the green carbons will be the ones which will lose the together OH and H, or the water molecule, and then they will form the double bond, right? So that's like basically going to be your reasoning. So I know it's several steps perhaps, right? So, okay, carbons and such, right? OH and hydrogen. So, but if you identify that in one alcohol, you'll be able to do it in other alcohols as well, right? So that's going to be kind of, like, again, reoccurring principle, right? So that we see here. Okay, so we have 2 carbons, right? So then let's imagine that they are going to have the red bonds, right? So made like that of red electrons. And now what's going to happen is that those bonds will be broken, right? So let's show it with a squiggly line, like so. So that's a squiggly line. So, and now what's going to happen is that you need to think about which bonds will be formed, right? So yeah, basically here, you are going to form 2 new bonds, right? So one of them will be the carbon-carbon bond made up of those 2 red electrons. First of all, of course, you need to break the CH bond and OH bond, right? So they will be gone, right? So, and now let's imagine that at some point you are going to have something like that, right? So you're going to have your carbon, H and H. So these are those. So top H's, they will survive. So this methyl group, just leave it alone, right? And then you are going to have those kind of like red electrons like that, right? So that will happen sometime in the course of the chemical reaction, right? It will happen like very, very fast, pretty much, right? So they will not be just kind of like, okay, well, separate atoms, right? floating around, they have too high energies, they will need to kind of like be connected to reduce the energy, because generally in nature, right, systems will try to achieve the minimum of energy to achieve stability and such like that, right? So now also at some point, kind of like very intermittently in the reaction, you will have those like hydrogens, right, which are chipped away, and the OH. So, and then they will have their respective red electrons, right? So, and that's it. So now that's going to be your like yellow stage. That's going to be the intermittent stage. And you go like this, right? So you start, then you apply your conditions. So some kind of like transition situation happens, and then you are going to make the final products, right, of the reaction. So yeah, basically here you broke two bonds, CH and OH, and now you have those kind of like liberated electrons, right? Carbon red, H red, OH red. So like very good. So and now this hopefully will like let us understand how the bonds are formed, right? So they're formed just by connecting those electrons, right? So you make this connection. So then you make all of a sudden carbon-carbon double bond, which will correspond to your alkene, right? So, and now if you connect, I'm kind of doing this like sloppily like that, right? So H and OH, you are going to make the like OH bond in the water molecule, right? So now if you like draw that normally, you will get the HOH, okay, that's properly drawn. And now if you like make this like a better bond, then you will make the alkene, right? So CH3, leave it alone, right? So then you'll have a CH piece and CH2 finally. So that's going to be your like alkene that you are going to form. So that's your like breaking and making of the bonds, right? And then it corresponds to the proper chemical reaction. So now let's see, that's going to be the dehydration of the alcohol, right? So we basically go from an alcohol to an alkene, right? So now let's imagine that we are going to have the like opposite situation, right? So hydration, so like we can call it in other words, the synthesis of an alcohol, right? So I'm going to just show it here on the projector screen. So because this, I complained so much, so and then like, they only removed the recording, right? So like capability, which I don't need anyway. So yeah, strange things happen sometimes, but okay, well, I guess we keep going. So if we take a look at the hydration of the alkene, which is going to be tied to activity number 2, finally, right? So here I'm gonna show like a very simple example, right? So that you can make something difficult. So that's going to be like alkene that you are going to hydrate, right? So just show for your education purposes the water molecule like that, right? So that will have the bond. So now, so some people said there was at least one response. Somebody said, I liked how the groups are like circled and colored, right? So like, well, let's continue doing that, I guess. So we'll have the carbon-carbon single bond, right? Maybe it is going to be the pi bond, for example, because those are broken faster than sigma bonds, right? And then we have this bond between H and OH. So that's what will happen in case of hydration, right? So you must have alkene and water as your starting materials. So then we are going to kind of like do the hydration. So we'll apply the conditions. So it's going to be H2SO4. So that's like one and only acid that we use for the hydration like conditions. So now we are going to show the bonds which will be like broken, right? So this will be like this one will break, and this bond will break as well. So now the result will be on the right side. So we are going to redraw. So let's say sigma bond stays, right? So just leave it alone. That's going to be your sigma bond. So then carbon. So these are your H's, right? So the original H's, they're now in purple for some reason, but yeah. I think you should be able to track those H's, right? So, and now you have those kind of like blue H's and the blue OH group. So, well, where are they going to be? So now we have those liberated electrons, right? So, and now we also have the liberated electrons on the H and OH. So they are still kind of like red. So, and now we're going to make the bonds, right? So here we just make single bonds. It's going to be CH, that's one, and the COH. And here you made it. So that's going to be your alcohol, right? So notice how you change hybridization. So it could be like a good question on exam. What's the like hybridization here, right? What is it there? So geometry on this carbon, geometry on that carbon, right? So again, these are all like reoccurring questions. So that's going to be the hydration of the alkene, and that's it. So you only have like one product at the end of the day. So you can call it an addition reaction. So because you just add like A plus B becomes AB, right? So that's the principle. So if you count all the like types of atoms on the left, and the right side, it is just going to be the combination, right, of them. So there was like nothing was like removed or switched, exchanged. So like not of that stuff, right? So this just kind of like stays there, right, as conditions, and that's it. It's just like chills, right? So, but it needs to be shown as well. So to like for the, because without this H2SO4, the reaction will not go, right? So that's why we need to care about those conditions. Or maybe it will go, but very slowly, right? And it's going to be like not proper. So now, finally, activity number 2, hydration of some alkene, right? 6 carbons total that leads to the formation of an alcohol. So pretty straightforward. So let's see. So like we want to try to give way to some new people. So hydration of alkenes. So like pretty good question. So let's see. We'll give chances. So let's think about that. So yeah, again, you can like earn extra points, right? It's like not so bad. It's very similar to that, right? So that's why we have this sort of like pattern building, right? We show something, okay, well, that's how some random alkene will react. So then you can like make your own alkene and make it react. So that's going to be the whiteboard activity. All right, so we, I think, have enough time to think. Okay, well, you're first. Let's go then, and alkene of your choice. So now it's going to be one of your peers that will demonstrate the, maybe the blue color. You want? Oh, let's do the expanded one. So yeah, that's okay. 20 minutes. All right, so let's see what's happening. Even though the drawing like goes horribly wrong, right? Just for the future, right? So you'll still earn the points. So yeah, typically, like historically, it was fine. So there was only like maybe one case which was like very off, right? When people were drawing some like reactions or stuff. Okay, that's a good adjustment. And then you are making the, yeah, you need to have the alkene. So it could be like double bond can be anywhere as long as like makes sense, right? So. All right, so yeah, that's good. So we have the alkene, and then it looks proper, right? So yeah, now we're going to hydrate it. So that's your water molecule, right? So let's see what happens. So yeah, here you have the kind of specific placement, right, of the double bond between the carbons like 2 and 3, right? It is going to be 1, 2, 3, 4, 5, 6. It's going to be like 2 hexene, right? By the way, from the nomenclature perspective, you just need to make sure that the like OH stuff lands where it needs to, right? Not it needs to be like on the like a respective carbon and hydrogen. So let's see what we get. You can use a different color to show those kind of like H and OH added, right? But yeah, it's fine at this point. So, all right. So like, looks like it's all good. So we have 6 carbons, and then the double bond is between carbons 2 and 3. And then your OH and then H will be also attached to the carbons 2 and 3. Okay, that is good. So here we have, what do we have? So like we have CH and we have another CH for the alkene. So yeah, at this point, you just did the addition reaction. So that's all good, right? So theoretically, you can make an isomer, right? So in this situation, right? So in this case, so if you, by the way, like let's think about this question. That's going to be like a good starting point, right? So if you take a look at this alcohol, right? So it could be potentially like an exam question as well, right? It's a little bit more about the like expanded thinking, right? So that you can use in your chemical reactions reasoning. So here, what was shown, I don't remember all the names, unfortunately. So, but here we have it, right? So we have, so let's say the count, right? So we need to minimize the numbers and such. 1, 2, 3. Have 4, 5, 6, right? So it's going to be 2 hexene, right? So carbons 2 and 3 have a double bond. So that's where the OH, H and OH will land, right, from the like water. So here you go. So you basically got OH here on the second carbon, and then this third carbon got the H, right? So here we have it, right? So that's one possible molecule, right? So that's going to be the keyword here, one possible molecule. It's going to be the like alcohol, which has the OH on the second carbon, right? So it's going to be, in this case, 2-hexanol, right? So 2-hexanol. So now let's see. There's going to be the question. So what is another isomer? Another isomer, right? So that will be possible. Okay, so let's think about it. So like where else can we, what kind of isomer can we make here, right? So isomer to the product that we show here. So in this case, we have like 1, 2. It's going to be 2. On carbon 2, there is a alcohol, right? And then it is like present on the 6-carbon chain, right? So which stems from the alkane, used to be hexane, now it is 2-hexanol. On carbon number 2, in hexane, there is the like alcoholic stuff going on, right? So it is 2-hexanol. So, but what is going to be another isomer? Maybe you can just call it, right? So like nomenclature-wise, so that's okay. That's going to be quite professional. In other words, or like if anything, okay, so what is another isomer, right? So because if you think about that, so you can like go this way or you can go like that way, right? So with your H and OH, that's one, or maybe like another way. So I'm just trying to make some hints with my hands, right? So maybe this will be helpful, who knows? All right, so we have the HOH addition, right? So, and then those electrons will just need to be connected, right? So to make the bonds, so they don't quite distinguish that, oh yeah, OH must go to that atom. So that's just one option. It's a good option. So yeah, tremendous choice. But we might as well have some isomers happening here. All right, so let's take a look at what we got here. Okay, so looks like switching H and OH, right? So that's what we will have. So that is an option. So we can definitely switch them, right? So it's going to be going now to position number 3. That's the one. It's going to be going to position number 3. So notice, so there are some answers that say in 1-hexanol, but it will be impossible because this like carbon number 1 stays, just let it be, right? So it doesn't participate in the chemical reaction. It's only going to be this kind of carbon-carbon double bond which will participate in the chemical reaction, right? So that's why we kind of like say it specifically, and that's what we need to pay attention to, right? So I don't say that, oh yeah, you can just attach it somewhere here, right? Somehow, right? So like remove 1H and then attach the OH. No, it will not happen, right? So you only pay attention to this carbon-carbon double bond, right? So that's what will participate in the chemical reaction by being broken and then like gaining H and OH, right? So then, yeah, that's right. So some people say simply switching, yeah, could help. So your either isomer will be like this, right? I'm going to show it here. So it's going to be a 3-hexanol. So let's show it this way. So 1, 2, 3, 4, 5, 6, right? And then you will have your OH here on the third carbon, right? So on the hydrogen will be here on the second carbon. So yeah, that's it. So that's a different isomer, right? Different placement of the building blocks. All right. So Now let's see if there is any more charge left in the iPad. So, or maybe it's completely dead. All right, so now it's going to be the great change of the screens, I guess, and we are going to take a look at the screen of the laptop. All right, so just a second. All right, so we have, I think, some more reaction types here. So yeah, which will be a little bit different laptop HDMI. Okay, and then send it to the, that's going to be the left projector. All right. Maybe I need to drag it. Drag it? Okay, yeah, that's right. So that's like what do we have? Okay, so next one will be, so we're going to take a look at the rules a little bit here. So, and let's take a look. So we have the hydration. So now we have the dehydration expansion, so to speak, right? So let's see what happens here. So in some cases, the like several products can be formed, right? So we are going to take a look at the dehydration like first from like bird's eye view or something. And now let's see what happens, right? In terms of the rules of dehydration in certain cases. So here we go. So that is gonna be our alcohol right here. So we have the alcohol, right? So which is kind of branched, right, and everything. And it will have potentially like several like places from which the H and OH can be eliminated, right? So in this situation, I'm just gonna redraw that on the paper, I guess. So, and then yeah, we're going to show the expanded structure, especially in the area which will potentially lose H and OH, right? So again, so we need to look at the adjacent carbons, right? So which will have the capability to lose water, right? So, okay, anyway, so let's start drawing finally. So these are your carbons, right? So one of them has the OH. So, but then if we are careful in our kind of approach in this situation, we will notice that we technically have, let's say, we used to call them green carbons, right? So that's a carbon with OH, right? Which will lose the OH upon dehydration, right? So because it will have to happen, right? So another carbon which will be losing the hydrogen and will have to be adjacent to the green carbon. But turns out we have two adjacent green carbons, right? That's one and this one. So as long as they have hydrogens, they can lose them, right? So now let's continue with the hydrogen count. So that's H, and then this is another H. And also notice that in case of alcohols, right? So all the carbons are originally sp3 hybridized, right? So they are kind of having this tetrahedral geometry, but then you'll be making the alkene. I'll show it here better. So there's some like error going on. So anyway, so we have hydrogens here on the carbons, so which we're going to show as well, and a couple more metals. So no need to expand them because these carbons, this one and that one, are too far from the carbon with OH, right? So we only look at the adjacent carbons that are connected with like one bond, right, to the carbon with OH. So these ones are too far, right? It's like don't touch them, basically. So and now here we have it, right? So we have two options in this case. So okay, so we have two options to remove the H and OH, right? So option one. So let's say it's going to be like that. So we are going to remove the OH, right? So that's one. And the other one will be this one, right? So that's going to be one possibility to make an alkene, right? So, and then let's see what happens. So if this pathway works out, so it's going to be, let's say, pathway number one, let's call it just option one, right? So you're going to remove OH and H. So it looks very legitimate, right? So you're going to make an isomer, right? Out of the two possible like isomers that you can kind of like conceive in this case. So what are you going to make in this case? You're going to make C with a couple H's, right? So CH2. Then we can show double bond right away. So these are used to be our like green carbons, right? So that's a green carbon here. So then the OH is gone. So consequently, it's only going to have the H left over. Single bond, then this CH stays, right? So because you remove HOH, only one water molecule, and that's it, right? So you are here, right? So that's one possibility, right? So if we just think critically about the situation. So now another option, right? So let's call it option 2, like pathway number 2. So you are going to remove, this is going to be OH and this H. So it also gives you water, right? Removal option, HOH. So, and then you leave this H kind of like intact in this case. So what are we going to form? It's going to be the following thing, right? So we're going to make this like CH3. This will prevail, right? So then carbon will only have now H. So this OH will be gone. So consequently, we will have like a new bond formed. So this carbon will lose hydrogen, right? So to make water, and then it will have the leftover methyl groups. All right, so these are gonna be like our options to form, right? So two opportunities, right? So what's going to happen now? So like we will have two isomers, right? So let's say isomer is going to be like A here, and isomer B will be formed. So turns out one of them will be major, one of them will be minor. So both of them can be formed, right? So, but one of them is major, meaning it will be present, let's say like 95% of the mixture will belong to one of the compound, right? The minor one will be like 5% in the mixture. So it turns out that the major one will be compound, what's it? It's going to be a compound B, right? So A will be the minor. So what happens? So we need to count the substitution, right? So that is kind of like present on the alkene double bond, right? So let's count, right? So like what we are going to look at here is how many other carbon groups are attached to the carbon-carbon double bond, right? So for our convenience, let's choose another color. Maybe it's going to be, let's make it orange, for example, right? So we're going to like spot the carbon double bond. Okay, that's 1 and 2, right? So like no problem here. So they all used to be kind of like green atoms, by the way. So that's the green atoms that participated, right? So, and now we're going to count the carbon groups, carbon chains attached to the carbon-carbon double bond. So let's take a look at compound A, right? So here we only have H, it's not carbon, H. So only one carbon containing group is attached. So that's going to be circled in the orange color, right? So now if we take a look at compound B, so here we have the double bond, right, between two carbons. Okay, good, we found it. So now let's count the carbon containing groups attached to the carbon-carbon double bond. So here we have it, right? So it's going to be one carbon containing group, another one, and finally carbon containing group number 3. So you will total have 3 carbon containing groups attached to the carbon-carbon double bond. So consequently, this product will be the major. So because it has 3 alkyl groups attached to that, right? So as opposed to only 1 alkyl group attached to compound or isomer A. So basically, the more kind of like alkyl-based substitution you have, right? So the more chances that this will be your major product. So that's going to be the reasoning behind this Zaitsev's rule, right? As they call it in like other terms. So that's like what we need to pay attention to, like not the hydrogens, right? So they will not count as the alkyl groups because they're literally hydrogens, right? So just kind of like don't count them as carbon containing groups. So, but you need to pay attention to the carbon containing groups. This guy, right, it's going to be technically called isopropyl, right? So this is a literally carbon containing group, right? So as well as methyl, then methyl and methyl, right? So they're all carbon containing groups. So yeah, that's like what we will have. So now we need to show the dehydration well, I guess we are done at this point. So yeah, let's stop here and then we'll carry on to Thursday, like all other slides. All right, so if you did the extra credit, stop by, put down your name, and we'll be all set. So I'm going to stop the recording now, and let's see. Have a good one, everybody.